Welcome back. So, now this is our first case study, and this is as you can see the title of the paper, and I have given references for this in your material. So, you will know this paper, a combined molecular dynamics and Raman spectroscopy approach for designing ice metal interfaces. The key word here is designing, because most of the design that have been done of the materials like de-icing coating, de-icing materials have been done by what we call is rule of mixture. So, you will arbitrarily create those polymer coatings, mix them, test them. There is no rational basis for it. There is no atomic basis for it. So, we are now going to use this to come up with an atomic basis for it. So, first thing what we did is that we looked at lots of different metallic surfaces. I looked at titanium, aluminum, copper, and also Teflon. So, we looked at not only metal, but also non-metallic, because we were looking at the adhesion of the material. And this is a setup that we created. As you can see, this is a microscope, and at the bottom there is this surface, and there is the cooling. So, we had a cooling system which is based on thermoelectric cooling. So, we could cool material to very, very low temperature, this metallic surface, and then we introduced the vapor from the other side, and there was a glass window where we can then shoot the laser inside, and then we could measure the Raman spectra. And let me remind you, we did talk a little bit, but Raman spectra is about what we call molecular spectroscopy. So, it tells you about the vibrational modes of the molecules. So, as you know, using velocity autocorrelation function and Fourier transform of that, we were able to calculate the what we call a generalized vibrational spectrum. The same situation is here, but this is using experimental method. So, I came up with optical cell for a spectroscopy apparatus to understand first in a practical way, in a experimental way, what is happening to the vibrational modes of the ice as it is being deposited on the copper surface. So, we have a copper surface, we cool it down a lot, and then slowly we deposit ice, and we see the deposition of ice on a very cold 70 degrees Kelvin copper surface, and we were able to see layer by layer by layer. And remember that layer by layer by layer formation of the ice and vibrational mode. So, as the layers became thicker and thicker, right from very, very tiny micron size all the way to few hundred microns, we were able to follow how the crystal structure was changing, because we are looking at their vibrational modes. So, if you are in a crystal structure, there is certain vibrational mode, and so if you are in amorphous, you have a different vibrational mode. If you become liquid, it is a different vibrational mode. So, that was number one thing that we have to understand about ice. So, if you look at for that purpose, we use also for molecular dynamics simulation, we have to understand how are we going to calculate the water potential. And as you know, in my previous studies and the previous sections, we have seen how we took a thin layer of ice with 8 layers, and we were able to figure out the different modes that lead to the breaking of the ice bonds before the ice melts. And I do have a paper reference for you where we looked at what are the mechanisms of breakage of the ice based on the molecular dynamic studies. So, looking at that, now there are two parts, interatomic and intraatomic. We already know about it. So, here you have OO part, which is a Lennard-Jones, Coulomb, and this one is bonded material, where between OH1, that means oxygen and hydrogen 1, and oxygen and hydrogen 2, we have this complicated intramolecular interaction, which is bonded material. And then these are all the parameters which Toucan and Rahman did a lot of experimental research to come up with all these values in terms of the Coulomb constants. All of these constants A and C, they are all defined based on the calorimetric studies of specific heat, etc. So, there are a lot of thermodynamic properties, lattice constant, sublimation energy, melting point, all of these ideas are put together. And then we also look at from some of the studies done on the bond lengths. We now have the OH bond, HH bond, and HOH bond, and we are combining them. So, in this problem, now you need to know each bond length and also the constants which are the spring constant. So, with the spring constant with the bondage, if you remember the bending and the stretching and the rotation, all of that is combined. So, this is very detailed simulation of water particle, and also in terms of electrical charges, because water does have electrical charge on oxygen and hydrogen atom. For that simple point charge, we were able to use that using Ewald summation procedure. So, we did the long calculation and did the Ewald summation, which was a separate subroutine in the program. So, now we want to set up this system. So, this is how, if you have to solve this problem as a scientific investigator, you are going to first set up your model, set up the scene where you have to investigate. So, now in this case you have a bunch of water molecules on top of this copper surface. So, if you look at, this is the simulation cell which has two parts. One is the water part with ice molecules, and they are put in very regular crystalline structure, and this is cubic ice, and below that we have face centered cubic copper, and we are using 64 atoms or 64 molecules of water with 192 atoms, and then we are using almost 216 particles of copper which are forming 6 by 6 by 6 block of copper. And as you know, before we started this experiment, we first made sure that the water potential is calibrated and works well. We also made sure that the copper is calibrated and works well, and that this is how we set up the system. 8 layers of 64 water molecules, because we want to look at layer by layer by layer. Now, remember, we had done the experiment using laser microprobe spectroscopy, layer by layer of ice. We are now looking at layer by layer of ice in the simulation. So, what we did experimentally, we are simulating in terms of atomic level. So, this is the same model. We looked at the 6 layers of copper with Foils, Baskis and Doe 1986, and then we also looked at SPC potential with Tukan and Rahman, and then the third potential water and copper interface was designed by myself, where I came up with the cluster calculations on these particular particles, and then there were 50,000 time steps with all these 2 different interface formation and periodic boundary condition on x and y, but in z direction it was allowed to relax, because we wanted to see the relaxation of the particle in z direction. So, this is the interface potential for bimaterial interface. We looked at lot of data and fit these parameters, and we found that with the binding energy curve it was very good fit. So, we said it is a reliable interatomic potential function based on the cluster of atoms of the copper, and putting this one ice molecule or water molecule, taking it from a particular distance, getting right close to the conduction electron and seeing the cluster quantum mechanical interaction between linear combination of atomic orbitals in a self consistent field theory. And you have more details in the paper that you can refer to in the reference. So, this is how this function is created. I quickly went through the R, the atom distance, and rho is the projection of the distance vector on the surface plane respectively. This model uses total 8 A and beta parameters. So, as you know, for creating this I looked at lot of experimental data, and we have 8 A and beta parameters. So, now what we have done in this case, we looked at first the Raman spectra of the ice in 2 areas. One is in the lattice vibration, another one is high frequency vibrations. So, let me stop here, because I want to take you through why we are doing in terms of lattice vibration and the high frequency vibration, and we will get back into the rest of the investigation. Thank you.